All right, so we are looking at systems of equations, and today we're going to solve by graphing, which we'll get to in a second. But let's start with these two definitions that I already wrote on the board. So, system of linear equations. This is really just a general definition for what we're looking at for all of chapter 6. So, we are looking at two or more equations containing two or more variables, right? So, when we're graphing today, instead of graphing one equation on a coordinate plane, we're going to graph two equations on a coordinate plane, right? So that's two equations with two variables. As I mentioned, like when you get to Algebra 2 or pre-calculus, you will look at three equations with three variables, and if you continue studying math in college, you look at all sorts of stuff, which is pretty fun. And then, once you have your system of equations, and we're going to stick with just two variables, two equations, then this solution is specific to our two equations. And so we're looking at, it's just simply an ordered pair, right? That satisfies both equations, and by that word there, satisfies, I mean it makes the equations true. That's what, in math speak, that's what satisfies means. It means that you are going to make your equations true. And that's the same thing like when we solved in chapter 2, when we solved x plus 2 is 12, we know that x is 10, and when you plug in 10, you get 12 equals 12. So you made the equation true, right? You got a true statement. So it's the same thing, but now instead of plugging in one number, you're going to plug in an ordered pair. So an example of what this solution looks like is if we had this system, so the system could be y equals 5x. That's one equation. And the other equation is y equals 1/2 x. Well, these are only going to intersect once, right? Or they're only going to cross once. So what we're looking at is this is the solution. And to see how that works, you could just plug in 0 for x and 0 for y and see what comes out. So let's do that. 0 for y equals 5 times 0x. Yep, 0 equals 0. That's a true statement. So it worked for the first equation. Do the same thing. Plug in 0 for y. Plug in 0 for x. Yep, 0 equals 0. That makes 0, 0 a solution to the system. If you plug it in, you get out a true statement. Yes?
So, like, it can always be 0, right?
For this problem, yes. For all problems, no. It's always interchanged. For this particular problem, 0, 0 is a solution, right? You plug in zeros and it works. And this is actually the only solution to this system. Yeah?
Is there like a simpler way to solve that? Like to solve, like
not
specifically this problem, but like other.
Yes, so that's what today's class is on. We're going to get there in a second of how we come up with this answer. But for starters, let's just make sure we understand what it means to be a solution, because that's going to come up in every class period. And then we're going to break up classes in talking about different methods. So today's graphing, tomorrow's what we call substitution, Monday will be a different method. So we're going to look at different methods over the next 3 class periods. But identifying solutions, that comes up in every class. So let's go ahead and write this down. So our example 1, we're just deciding if the ordered pair is the solution. So for part A, you're going to look at the ordered pair 1, 3 and decide if it's a solution to this system. 2x plus y equals 5 and negative 2x plus y equals 1. And then with part B, let's go with 2, negative 1. And here's your system. X minus 2y equals 4. 3x plus y equals 6. All right, let's get some work up on the board. So, Miles, when we plug in 1, 3, so 1 for x, 3 for y, just this first equation, what do we get out?
You get 5.
Yeah, so that first one, you get 5 equals 5. Yep, that's definitely true. Okay, Porter, when you plug in 1 and 3 to the second equation, what do we get out?
1.
Get out 1, which is awesome. That's what we wanted. So this one is a definite yes. You plug in 1, 3, it works for both, so that makes it a solution. Jack, let's plug in 2 and negative 1. What happens when we do that to the first equation?
We get 0. No. Yeah. No. Positive 4.
4 or 0, which one?
4.
I like 4 there. Okay, 4 equals 4. Yep, it works for this first equation. And then Parker, if you plug in 2 and -1 into the second equation, what do we get out?
5.
Get out a 5, which does not equal 6, right? So that makes this one a no. So part A is a yes because it worked for both. Part B is a no because it didn't work for both. All right. So let's go into then how do we come up with these solutions, right? What do these look like? So what we want to see then is we're going to solve by graphing. And so ignore the example for right now. But what we're looking at is, so when you're graphing, a solution is the intersection of the graphs. Right? That's all it is. So I'd make a note of that when you are solving, or when you're graphing it, the solution is simply where do the two lines cross. And so as you guys do this on paper and on a quiz and on a test, I would go ahead and I would plot more points than normal. So I'm just going to say plot a lot of points to find an intersection. Because you're probably going to need more than 2. Although you get a unique line when you plot 2 points, to make sure you have a good graph, you guys are going to need to plot more than 2. All right? And then I'm just going to tell you guys that for any problem you guys see from me in class, on the homework, on a quiz, on a test, for graphing only, I guarantee the answers are going to be integers. So if you get a fraction as an answer, you know you're wrong when it comes to graphing. All right? So plot these points, right? Graph your y-intercept, count your slope. Where do these intersect? And then don't forget to check your work. All right, let's get some graphs up on the board here. So we'll this top line will be in green, bottom line will be in red. So y-intercept of -1, slope of -2, down 2, right 1, down 2, right 1. I don't know how many points I'm going to need, so let's get a fair amount on the board. This is probably enough, right? Our intersection will probably happen in one of these points. So there's our line. And then our next line, we'll look at +5 here. I could go up to the right, up 1, right 1, but that won't help us since the other line is down below. So let's go down 1, left 1, down 1, left 1. There's our intersection. We can see it right there. So it looks like our intersection happens at the point -2, 3. And anytime you guys are doing this, you should do a mental check. Plug this into your equations and see what you do. I'm actually going to do it on the board. You guys should at least do it in your heads. -2 times -2 minus 1. -2 times -2 is 4, minus 1 is 3. Yep, that one works. 3 equals -2 plus 5. That one definitely works. We did it correctly, right? We plug those in and it works. So now let's do the same thing. Let's graph the other one. Plot your y-intercept, -3. A slope of +1/3 here, up 1, right 3, up 1, right 3, a little bit off the graph, down 1, left 3, that was left 2 here. Graph should look like this. And then our other equation, and this looks like we can go ahead and plot using intercepts. The y-intercept is going to be a 4, plug in 0 for y, the x-intercept's a 2. And it looks like they're going to intersect here, but we can't be 100% sure. So let's change this to slope-intercept form just to make sure. Down 2, right 1, down 2, right 1, down 2, right 1. Yep, that is where they're going to intersect. So this is our intersection point. This is the point 3, -2. To make sure, plug it in. So -2 equals 1/3 times 3. Minus 3. 3 times 1/3 is 1. 1 minus 3 is -2. Yep. And then 2 times 3 minus 2 is 4. Yes, that one also works. So make sure you guys are checking these points. Plug them in your head at least. Make sure that they work. All right. And then make sure you're plotting enough points so you can see a clear intersection. That's all we need to do. This is really just a practice in graphing, right? You get to 2 graphs per problem. That's really all solving by graphing is. Make sure your graphing skills are strong. So to make sure they are, let's go one more problem and solve these 2 systems by graphing. Let's get this first one down now. It's in standard form, but it's not a great way to graph, given that if you found the x-intercept, it would give you a fraction, right? And we don't want that. So let's change this to slope-intercept form. Somebody raise their hand and tell us, how do you turn this into y equals mx plus b? Denise? Okay, so minus 4x from both sides. And then?
Divide 2 by this.
All right, divided by 2. So we get a y equals negative 2x plus 3. This is going to be your easiest way to graph this particular line, so let's do that. Y-intercept of 3, slope of negative 2, down to right 1, down to right 1. Let's just make sure we have enough points here. That's probably good. There's our line. And then this one's already in slope-intercept form. Easy to graph. Y-intercept of negative 1, down to right 1, down to right 1. All right, what kind of lines do we have here? Parallel lines. When do parallel lines intersect? Never. But they do make this nice little pattern here, so we can write no solution right in the middle. There we go. So parallel lines definitely never intersect by definition, so they will never have a intersection point, right? No solution is going to be our answer here with parallel lines. No solution. Now with our next two, these are written in a form that I would just leave them in standard form and find your intercepts, right? That's going to be your easiest way to graph these two. So we can quickly see that if you plug in 0 for y, our x-intercept is 4. Plug in 0 for x, your y-intercept is 3, right? And it looks like that'll probably be enough points, because if we find the x-intercept here, plug in 0 for y, you get out a 4 for x. Plug in a 0 for x, you get out a 3 for y. You have the same intercepts, which means you have the same line. So these are one on top of the other. So when you have parallel lines, equal no solution. And then in this case, we have the same line equals, and we're going to call this infinitely many. Because there's an infinite number of ordered pairs, but you can't say all real numbers, because all real numbers is referring to one number at a time, right? Like 5 or 7 or pi or whatever it is. We're talking about ordered pairs, so we're going to say there are infinitely many solutions, and it's just every ordered pair that is on this line. Yes?
Are we going to do this on homework? Like, how would we say if there's infinite numbers?
You would type in infinitely many solutions.
I hope there'd be some.
No, you're just going to type in infinitely many solutions. That simple.